Chapter 18 covers climate change and ozone loss. I wanted to start this video with a picture of the Minister of Fisheries and Agriculture of the Maldives. I'll explain why they're all wearing scuba gear at their desks shortly. For its 370,000 residents, the 1,200 islands that make up the Maldives are home. These islands are beautiful and people travel from all across the world to see the crystal clear waters. But the Maldives could soon be submerged by these same waters as they rise due to global climate change. Higher seas are expected to flood large areas of the Maldives and cause saltwater to contaminate drinking water supplies. Scientists expect storms intensified by warmer water to erode beaches and damage the coral reefs that are vital to the nation's tourism and fishing industries. This is an entire country that could be swallowed by the ocean. In North Carolina, we will see some of the same events as the barrier islands are flooded, but there are quite a few countries that will completely disappear off the map. Major politicians from the Maldives held an underwater meeting to raise global awareness of their flooded future. I wanted to start by saying that climate change is not a new thing created by the Chinese. You can go ahead and hang that idea up. It's considered a highly debated topic in places that aren't truly experiencing the full force of a warming climate, but the people of the Maldives aren't debating their own reality. Over the past 900,000 years, Earth's climate has seen many ups and downs. The downs are known as global coolings, or ice ages. The ups are known as global warmings. What we are experiencing isn't the global warming, but an episode of global warming the Earth has seen and survived through in the past. The time between two cooling events is an interglacial period. We have been in our current interglacial period for the past 10,000 years. During this time, there have been many shifts in regional climate, but we are starting to see a more drastic turn as of late. So how did we get the information to make these graphs if we haven't been around long enough to make them? Did our ancestor monkeys gather the information? No. First, we didn't evolve from monkeys. Hopefully you know that by now. Second, we have many types of tests we can perform, as well as a planet covered in evidence we can observe. There are radioisotopes found in rocks, fossils, and ocean sediments that we can observe the half-life of in order to determine the age of the area they are found in. These materials contain elements of the climate in which they lived or existed. We can also look at ancient water in ice cores. Remember that water contains dissolved gases and is constantly diffusing these gases into and out of the air. When the water freezes, bubbles of these gases are trapped inside. Almost the same idea works with tree rings as well. If you've ever looked at the rings of a tree, then you have noticed that they aren't all the same thickness. This is because the amount of growth the tree experiences in a growing season is directly proportional to the growing conditions it was in. If there was a warmer year with more rainfall, then the tree grew more than in a year that was colder and received much less rainfall. Last, we have historical records. These only date back but so far, but our ancestors, not the monkeys, did a great job documenting any outlandish climate changes. We can piece all of this evidence together to get a pretty good idea of what the Earth's past climate was like. We covered greenhouse gases and the greenhouse effect with the chapter 6.1 and 6.2 video. If you're rusty, then it might be wise to rewatch it, but in short, the atmosphere is warmed by certain gases that help trap some of the energy released by the sun and eventually the Earth in the troposphere. These gases are called greenhouse gases. The most prevalent of these gases is carbon dioxide. It's what we exhale and what plants take in for photosynthesis. Obviously, it's great in certain amounts, but just like with all the other greenhouse gases, if they are emitted in high amounts, then there will be an increase in global air temperatures. Carbon dioxide is released into the atmosphere by the burning of fossil fuels, deforestation, and motor vehicle combustion. It lasts about 50 to 120 years in the atmosphere and has the lowest warming potential of all the greenhouse gases. The warming potential refers to the relative ability of one molecule of a given greenhouse gas to contribute to warming. All other values will be expressed in relation to carbon dioxide. Carbon dioxide in the atmosphere can be reduced by switching to alternative energy sources and planting trees to act as carbon sinks. Next, we have methane. Methane is released by cattle, coal production, and natural gas leaks. It lasts about 12 to 18 years in the troposphere and has 25 times more warming potential in comparison to carbon dioxide. Methane in the atmosphere can be reduced by burning the gas as it is or capturing the methane as a fuel source. Both of these methods turn the methane into carbon dioxide. Nitrous oxide is released into the atmosphere by the burning of fossil fuels and fertilizer use. It lasts for about 114 to 120 years in the troposphere and has a warming potential 298 times that of carbon dioxide. Nitrous oxide can be reduced in the atmosphere by reducing fossil fuel and inorganic fertilizer use. Last, we have chlorofluorocarbons, or CFCs. These are released into the atmosphere by air conditioners, refrigerators, and plastic foams. They can last 11 to 20 years in the troposphere and 65 to 110 in the stratosphere, where they create the most damage. In its simplest forms, they can have a warming potential of 900 to 8,300 times that of carbon dioxide. Some single molecules of hydrochlorofluorocarbons can actually have a warming potential 14,800 times that of a single carbon dioxide molecule. Chlorofluorocarbons can be reduced in the atmosphere by switching to other forms of coolants. This has been monitored by the Montreal Protocol, which I will explain at the end of the video. The main drivers in the Earth's long past of climate change are known as Milankovitch cycles. These cycles are periodic shifts in the Earth's orbit and tilt, which change the direction, distribution, and intensity of sunlight reaching the Earth's surface. This is a natural thing, but it doesn't quite explain the drastic changes we have seen on Earth recently. Many scientists regard anthropogenic, or human-caused global climate change, to be the most important environmental issue of our time. The idea that humans might alter world climate is not new. In 1985, the Nobel Prize for Chemistry was awarded to a man that predicted that carbon dioxide released by coal burning could cause global warming. Since the 1750s, or the dawn of the Industrial Revolution, we have seen a spike in the amount of greenhouse gases in the atmosphere. This is due to fossil fuel burning, deforestation, and burning of grasslands, and the use of inorganic fertilizers in rice paddies. As we have seen these gas concentrations increase, we have seen the global air temperature increase as well. How do we know this is happening? The concentration of carbon dioxide is the highest it has been in the last 490,000 years, and potentially in as long as the last 20 million years. The 20th century was the hottest century in the past 1,000 years. The ice caps are melting. Glaciers that took thousands of years to form are melting, over something as small as a decade. And the sea level has risen 4 to 8 inches over the last century. While that last one doesn't sound like much, 4 to 8 inches of water all across the entirety of the world's oceans is a drastic change in volume. Now, for the causes, it is a combination of both natural climate fluctuations and human activities. How does the sun come into play? Just like the Earth, the sun goes through cycles as well, during which the amount of solar output changes. This plays into a positive feedback loop for Earth's global warming cycles. The Earth's surface, just like all things, has an albedo. This determines how much of the sun's light is emitted back into space through reflection. White or shiny surfaces like glaciers, ice caps, and snowy areas have high albedo. Albedo decreases when these icy locations melt because the land is transitioning from a white surface to a dark surface. This means that the Earth's surface absorbs more energy from the sun. This energy turns into thermal energy, which then heats the surface and speeds up the process of the melting of these snowy locations. How do the oceans come into play? If you think back to the biogeochemical cycle days at the beginning of the year, you'll remember that I kept emphasizing that oceans are a carbon sink. This means that they remove carbon dioxide from the atmosphere. The oceans actually remove about a third of the excess carbon dioxide we emit into the atmosphere. This is another example of a positive feedback loop. You'll remember from the water unit that water has a constant flow of gases in and out of it through diffusion. As water warms, it is unable to hold as much dissolved gases as colder water, so some of these gases are deposited back into the atmosphere. If we are looking at carbon dioxide in particular, then the increase of this gas, a greenhouse gas, into the atmosphere will lead to warmer temperatures, which will warm the water even more and cause even more carbon dioxide to be emitted. Noticing a trend? Global warming won't just impact dissolved gas levels in the ocean, but ocean currents as well. They will be altered as the winds change and the densities of the oceans change as well. How do clouds come into play? They have a slight warming effect as well, as they absorb heat and release it back into the troposphere. They also have a cooling effect as they reflect the sun's energy back into space. These are opposing effects, but the net gain or loss of heat in this relationship is determined by the time of day, the type of cloud cover, and the size and number of water droplets in the cloud. For example, thick clouds would reflect more of the sun's energy back into space and can cause a cooling effect as a result. Thinner, wispier clouds that you see on rather clear sky days are more likely to trap some of the thermal energy in the troposphere, but don't bounce much of the sun's energy back into space. Having more air pollution leads to more cloud formation because there is more condensation nuclei present for clouds to form around. This can intensify the effects from the last slide. Aerosols have been the biggest concern in the past, but have quickly dropped off the radar as they fall back to Earth rather quickly and have pretty much been taken off the market because of their potentially harmful effects on humans. An increase in carbon dioxide sounds like it could potentially be a good thing for plants because it will lead to higher production rates for them. They have more of a fuel source to create glucose through photosynthesis. The limiting factor here would still be the amount of water available. This would increase the carbon sink we see with vegetation, but there is some apprehension behind it. There are some critics that claim there would be a rise in plant-eating insects with warming temperatures, which would deem the increase in vegetation inaccurate. What about soil? Soil can take in more carbon dioxide, right? It's something we are currently looking into as a means of sequestering carbon dioxide from the atmosphere to slow global warming. We can enhance this effect by planting more trees, improving forest management, and creating more sustainable forests, as well as reducing soil erosion. Our concern here is that soils have a tendency to release the carbon dioxide they hold back into the atmosphere as the organic matter found in them decomposes. So, this topic is still highly debated. Now, how rapidly could climate shift? It all depends on the steps we take in the next few decades. If it is a moderate shift, then it may take place over a long enough time elapse that we could adapt our ways of life to adjust to the change. If it is abrupt, then it may not allow us to make the necessary changes for our survival, like growing crops in new biomes that are created, relocating people in areas that may be affected by sea level rise, or building levee systems to prevent large flooding events. It would be a huge fiasco. What should we expect to see if the climate changes? First off, the water across the planet will be distributed differently. We will see changes in the global winds and weather patterns associated with them that will change up the levels of surface and groundwater across the globe. Because of this, plants and animals will be distributed differently as well. They will follow the water. Again, if it's a drastic change over a small time frame, then plants may not be able to migrate quickly. Overall, we can expect to see massive extinctions. The term global warming doesn't necessarily mean that every inch of the globe will be warmer. It just means that the overall average global temperature will rise. These changes in temperatures will lead to changes in the wind patterns, which will lead to changes in ocean currents and eventually lead to changes in microclimates associated with these ocean currents as well. Water, as with all things, expands when it warms, so we will see an increase in sea level as well. People seem to think that the only source of sea level rising is melting sea ice, but there's actually a lot more concern with the overall increase in volume of the ocean because of thermal expansion. As I said, we will see drastic changes in weather patterns erring more towards the extreme. And last, the temperatures could soar high enough that we, as humans, may not be able to withstand it. What are our solutions as of now? There are 4 major ideas here. Do nothing, do more research before acting, act now with a precautionary approach, and act now with no regrets approach. So doing nothing needs very little explanation. It's pretty obvious. You're doing nothing. Doing more research before acting sounds reasonable, but with the positive feedback loops I have discussed, we may reach the point of no return before our eventual actions take place. With most means of pollution prevention, acting now with a precautionary approach is the way to go. It is environmentally effective, but also cost-effective as well. And acting now with no regrets is the scary approach. If we do nothing now to stop the rising temperatures, then this will have to be the decision we make in the future. It will be extremely expensive and may not even work by the time we get desperate enough that the population as a whole sees the need to act. It's honestly fairly depressing. So what are we actually doing now? More than you probably would think, to be honest. In 1992, there was an Earth Summit in Rio de Janeiro in which 106 nations signed and approved a UN Framework Convention on the climate change. Signing this agreement meant that the industrialized countries would do their best to take the lead in reducing global warming within the next decade. It was not required and not effective, but at least made the issue more publicly known. This agreement also tried to ward off the idea of waiting for action until there was more scientific certainty on the actual cause of global warming. In 1997, in Kyoto, Japan, 2,200 delegates from 161 nations joined and agreed to cut greenhouse gas emissions. The major concerns with this agreement were that developing countries were not included in this treaty, and it allowed emissions trading between countries. In 2001, the United States withdrew their involvement due to these concerns. On Earth Day of this past year, 174 parties signed a document stating that they will reduce their greenhouse gas emissions enough that we can stop the warming of the atmosphere to lower than 2 degrees Celsius above pre-industrial levels. Scientists predict that at some point this agreement will require zero emissions from these countries in order to achieve this goal by the end of this century. Global warming isn't our only atmospheric concern. Here's where I want to say that global warming and ozone depletion are not the same thing. I will repeat. Global warming and ozone depletion are not the same thing. The ozone layer keeps about 95% of the harmful ultraviolet radiation emitted from the sun from it hitting the Earth's surface. By using balloons with instruments, aircraft, and satellites, we have discovered that there is a seasonal thinning of ozone concentrations in the stratosphere over Antarctica and the Arctic regions. There is also an overall thinning everywhere except at the tropics. Now, what is causing this? CFCs are the biggest concern here. Chlorofluorocarbons have also been called freon as well. That's probably the term you've heard of more frequently than CFCs. They are chemically stable, odorless, non-flammable, non-toxic, and non-corrosive, so they were seen as the dream chemical. They were cheap and safe, so they were used in products ranging from coolants to propellants to cleaners. But just like with DDT, CFCs were too good to be true. In 1974, scientists Roland and Molina discovered that there was a correlation between increased CFC levels in the atmosphere and decreased levels of ozone in the atmosphere. As a result, they wanted all CFC-containing products taken off the market immediately. CFCs remain in the troposphere because they are insoluble in water and chemically unreactive. Eventually, they rise to the stratosphere where their biggest harms come into play. In the stratosphere, they impede the natural production of ozone by capturing the UV radiation in its own reaction to create chlorine oxides. CFCs also cause ozone to break down very rapidly, faster than it can form in the first place. The company responsible for CFCs was DuPont. They said that Roland and Molina were crazy and over-exaggerating their findings. In 1988, DuPont finally accepted their fate and acknowledged their impacts on the ozone layer and agreed to switch to alternatives. How noble. CFCs aren't the only ozone depleters. We also have to be concerned about halons, methyl bromide, and carbon tetrachloride. Thankfully, none of these chemicals are used as frequently or in such a large abundance as CFCs were. Now, why do we see a thinning of the ozone layer over the poles? First off, what we often call an ozone hole is really a vast area of reduced concentrations of ozone in the stratosphere. We see this thinning more at the poles because of the winter months. Antarctica's exceptionally cold winter temperatures help break down ozone. During the long, dark winter months, strong winds, known as the polar vortex, isolate Antarctic air and allow stratospheric temperatures to drop low enough to create ice crystals at high altitudes. Ozone and chlorine-containing molecules are absorbed on the surface of these ice particles. When the sun returns in the spring, it provides energy to liberate chlorine ions, which readily bind to ozone, breaking it down to molecular oxygen. It is only during the Antarctic spring that conditions are ideal for rapid ozone destruction. During that season, temperatures are still cold enough for high-altitude ice crystals, but the sun gradually becomes strong enough to drive photochemical reactions. Why should we care about this? Lower levels of ozone lead to more sunburns, cataracts, and skin cancers in humans, and lowers our immune system responses. As for plants, we will see decreased yields in agriculture, the loss of phytoplankton that are essential for aquatic food chains, and decreased forest productivity. Wildlife will see the same effects as humans, but will suffer more from the harmful effects on plants, due to their diets being more specific. Humans can choose to eat something else, but organisms like deer aren't known to make such decisions. What are we doing to solve this problem? Here we have the Montreal Protocol. In 1987, in Montreal, Canada, 36 nations met and agreed to cut their CFC emissions. Notice that DuPont didn't agree that CFCs were a concern until after the convention made the problem a public affair. Again, noble. In the 1990s, the Montreal Protocol was strengthened to include other ozone-depleting chemicals as well. Unlike other forms of environmental law, this act has been extremely effective in reducing these pollutants. Now for a few AP tips. Tip number 1. Be careful that you don't state in answering your free response question that an air pollutant is bad because it is a greenhouse gas. Remember that without greenhouse gases, the temperature on Earth would be below the freezing point of water. Life needs the greenhouse effect. What most living things do not need is more of it. The addition of anthropogenic greenhouse gases is and because they enhance the natural greenhouse effect, causing global warming. Tip number 2. Stratospheric ozone depletion and global climate change are two different processes that are often confused with each other. The confusion is rooted in the fact that the newspapers and magazines we read, the television shows we watch, and some of the people we encounter in our everyday lives confuse the two processes. They are not interchangeable terms. Tip number 3. While they are the same structural molecule, remember that ozone in the stratosphere plays a different role from that in the troposphere. Stratospheric ozone is the so-called good ozone that protects life from the sun's ultraviolet radiation. Tropospheric ozone is the bad ozone that irritates our eyes and our respiratory systems, causes crop damage, and other causes as well. The instability of ozone molecules is necessary for both roles, good and bad.